Video, we're going to be going over port impedance in circuits that have feedback. So let's get started. So as I mentioned, we're going to be covering port impedance. So the impedance looking into a port could be an input of a circuit or an output of a circuit. So we'll be looking at port impedance in circuits that have feedback. So to start off with, we'd like to know if we're given a circuit and it has feedback, how the port impedance change in two cases, when the feedback is broken or when the feedback is intact. So imagining that we have a system like this here, where we have an input signal over at the left side here, p sub s equals 0. And we're interested in the impedance looking in to this node right here. So looking into this node, we'd like to know what is if we attach an ohm meter to that, what impedance would we measure? So, and in this circuit, we'll assume that there's a feedback loop shown here somewhere inside this circuit, and we've broken the feedback loop. So in this case here, the feedback loop's been broken, as we've shown here. It's the way we normally would break our feedback loop, by putting the appropriate impedances at either side. So when we do that, we'll assume that there's results in an impedance over here that we could analyze and find it's equal to Zin, comma 0. And the 0 is really here because this is for L equal to 0, for when the loop gain has been forced to be equal to 0. So we've broken the loop gain. In the second case, we look at the same circuit here. The only difference being now is that we're going to leave the feedback intact, so it's not broken at all. And we measure the same port impedance here. And we'll call that just Zin, and that's the one we'd like to find. So we'd like to find a relationship between these two, because this one's easy to calculate and do an analysis on. And how would we then, if we know the top one, how do we determine what the bottom one would be? So Zin would be. Okay, so let's look at this in a little more detail. So we're trying to find closed loop input or output impedance. So just consider a general circuit here. So if we have any type of circuit inside this dashed line here, so I've shown it as an amp, but it's any type of circuit. But let's say there is feedback in this. So externally, we show the line here, which is our feedback line. So this is feedback coming in. So we know there's feedback around this loop. So then we could model everything inside this as having an input impedance, a transconductance, and an output resistance. And then this is the port that we want to be measuring. So we're assuming that we've decided on a port here, Zin, relative to ground. So we're going to be looking at the shunt case here. So we're measuring it to ground. And we'd like to determine in this case, what does the Zin work out to be. So it's always a feedback case, and that's a feedback case because we have some sort of system which is unidirectional. So we're assuming it's a unidirectional feedback loop, and it goes around like that here. And remember we've zeroed our input, so there is no input anymore. The input has been zeroed, and so therefore we'll just have a unidirectional feedback loop somewhere. So assuming our port is left open, so we're looking at this here. If we leave this open, so if we just break this connection right here, and we say what would be the loop gain here? We'll define this as LOP. So the loop gain when the output port is broken or open circuited. Then the loop gain is just going to be the GM, the GM V1 times the impedance we see at this node here, which will be R1 in parallel with R2. So we'll see R1 in parallel with R2. So you can find the loop gain. We've seen how to do this before. You'll find the loop gain for this is just equal to GM times R1 in parallel with R2, which can also be written as GM times R1 R2 divided by R1 plus R2. So we can rewrite this as the GM, just taking this equation and rewriting it, is equal to R1 plus R2 divided by R1 R2 times the loop gain when it's open circuited. Now by definition, we have that Zin can be found by applying a voltage Vx and measuring the current I sub x. And by definition then, Zin is equal to Vx divided by Ix. So what we have then is that Ix, if we look at this, is equal to Vx divided by, so it's equal to this current, which would be Vx divided by R1, so the current flowing down through here, so it would be Vx over R1, plus the current flowing down through here, which will be Vx over R2, plus the current flowing down through here, which is Gm times V1, but in this case V1 is equal to Vx because we've applied Vx here, and that's then equal to V1. So if we just rewrite this, we have that Ix is equal to Vx times all of this term here, where we've replaced Gm here with this part. And that's why we now see that this is now our GM over here. Just rewriting that a little bit more, we have the next statement, the next equation, which is shown here. And so we can rewrite that one last time. We end up that Ix is equal to R1 plus R2 divided by R1 times R2 times 1 plus L, the loop gain when it's open circuited, times Vx. Now solving for Vx over Ix, we can rewrite this as this equation. Finally, we recognize that this part of the equation is R1 in parallel with R2. So we can finally write the input impedance is given by this equation here, R1 in parallel with R2 divided by 1 plus the loop gain when it's open circuited. So let's define a new parameter, Z sub in, comma 0, when the loop gain is equal to 0. And that would be equal to R1 in parallel with R2. So we're defining Zin equal to this. So in this case here then, what we see is that we're defining the impedance looking into this node when we break our loop gain, and we can break our loop gain just by setting Gm equal to 0 here. If we set Gm equal to 0, the loop gain is broken, all the impedances are set correctly, and we just find that Zin is equal to R1 in parallel with R2. So Zin comma 0, if we looked at the circuit, would be equal to R1 in parallel with R2, and so it's been defined to be that. So what we then can rewrite is that the actual impedance is equal to Zin comma 0 divided by 1 plus the loop gain when it's open circuited. And that's a general result then. And that's just to remind you that LOP by definition is the loop gain when the port is open. So if we ever have a case of a shunt impedance, and we'll see a series impedance in a second, but if we have a case of a shunt impedance where we're finding the impedance relative to ground, like this, then this would be the correct formula to be using. The one at the end, which would be right here. Find the impedance when the loop gain is opened or broken, and then divide that by 1 plus the loop gain when the port is opened. The second case we want to look at is find the port impedance when the series case. So in this case here, we actually have the port being now in series with our loop. So that's where the shunt and the series part is coming in. In the shunt case, our port was in shunt to the loop. Our loop, remember, is this wire here that's going all the way around. But in this case here, we've actually put our port impedance here and then back around. So if we short this port, we would have our normal feedback loop. If we left it open, we would have broken the feedback loop. So that's why we call this a series case. So we'd like to find in this case what would be Z in, and applying again either a voltage and measuring the current, or in this case we can apply a current and measure the voltage that appears, Vx. You can do either one. In this case, just decide to use the current, make it a little bit easier. So in this case now, we'll define the loop gain when the port is shorted. So when these two are connected together, I'm ignoring anything that we've gotten to the right-hand side here, our loop gain then will be the same as the loop gain was in the previous case. It'll just be GM times R1 in parallel with R2, because we'll have the same circuit. And then as before, GM will be equal to R1 plus R2 divided by R1 times R2 times the loop gain when the port is shorted. Once again, dividing Z in as Vx over Ix. And in this case, as I mentioned, we're using a current source input and measuring the voltage that appears, or determining what the voltage is. We can write down that the voltage V1, which is the voltage which will appear at this node at the top left corner, will just be this current I sub x is flowing this direction, which is flowing this direction, and therefore flowing this direction. So that voltage will be minus I sub x times R1. So V1 on the left side is minus I sub x times R1. The voltage on the right side, V2, will be I sub x. So this current now is also flowing up through this way and this direction. So it's going to be the current I sub x. The current that flows down here will be I sub x minus this current. So we can write this out as I sub x minus GM V1 times R2. And just moving those, combining those together, we have that V2 will be I sub x R2 minus GM V1 times R2. We can then take the substitution for V1 that we have up over here, put that in for this V1, and rewrite this equation. So now we have that V2 is now given by this equation. We can then replace the GM term here by what we have up here. And we end up with V2 is given by this equation. Now, finally, we have that the actual voltage we're trying to find is V2 minus V1. So we want to subtract this voltage and subtract this voltage, which would be adding that voltage. If we do that, we'll find that Vx is equal to Ix times all of this. And then finding the actual input impedance, which is Vx over Ix, will be given by this result here. So that means that we have that the input impedance is R1 plus R2 times 1 plus the loop gain when the port is shorted. So in this case, rather than defining Zin with the loop gain opened, with the loop gain set to 0 as R1 in parallel with R2, in this case, if we look at it, once again, if we zero our loop gain, we would set GM here equal to 0. So what would be our impedance Zin when we've set GM equal to 0 or set L equal to 0? In this case, we'll actually see R1 going to ground and then in series with R2. So in this case, the way the port is, because the port's in series, we'll actually have that Zin, comma 0 is now equal to R1 plus R2. So it's the impedance looking into the port when the feedback loop again is broken inside. So GM is equal to 0, which means L is equal to 0. Now because Zin naught is equal to this, we see this occurring right at this location. So we see R1 plus R2 occurring here. We can combine those two, and we have that the result in this series case is that the input impedance is equal to the port impedance when the loop is broken times 1 plus the loop gain when the port is shorted. And as I mentioned, L sub SH here is the loop gain with the port being shorted. Now we did it for the case when we're looking at a shunt on the feedback loop and a case when it's looking at a series one. Turns out we can actually do it in general. So I'm not going to prove this, but I'm just going to state it. But it turns out that in general, for any port in a system, that the actual port impedance is equal to that same port when the loop gain is broken, so the L is equal to 0, times 1 plus the loop gain when the port is shorted, divided by 1 plus the loop gain when the port is opened. So these are all the parts we just mentioned. This L sub SH is the loop gain with the port shorted. L sub OP is the loop gain with the port opened. And Z sub PO is the port impedance when the loop is broken inside the amp with our normal method of breaking the loop gain. So L goes to 0. And then with the correct impedances on either side. Now generally what you'll find is you can usually move, if you have a port that you want to find an impedance, that port could be far away from the loop, could be not that close to the feedback loop, but you can generally move that port closer to the feedback. And if you do, then you'll find that one of either L sub SH, the loop gain when the port shorted, or L sub OP will be 0, and the other will just be your standard loop gain. And that will make life a little bit easier. Okay, so let's look at some examples on using this in some circuits. And by the way, this avoids the need to try to figure out whether it's a shunt or a series shunt or all that sort of stuff. Things will just come out in the math here and things will work out. So we'll start off with this example here. We have a transistor here, and we'll assume that R0 goes to infinity just to make our life a little easier. And we'll also assume that Rs, which is 1 over Gm, is equal to 2 here. So we'll just use simple numbers here. We'll use 2 for Rs, we'll use R1 here to be 1, R2 to be 1, and we'll have an amplifier and feedback here with a gain of 10 over here. And we note that it's negative feedback because we're attached to the negative terminal here, and the gain from this point to this point is a non-inverting because it's a source follower. So we have one inversion around the loop. And we want to find the port impedance shown over here. So it happens to be a shunt attachment, but we don't have to worry about that. We just do work through the analysis, and that will come out naturally. So let's find out what the actual answer is if we do nodal analysis, and then we'll see how that compares to doing loop gain analysis. So to do full nodal analysis, we can first replace this transistor here with the T model, just to make things a little more straightforward. So replace that transistor here with the T model. So this becomes the T model for that transistor. And if you notice, we have RS equal to 2 here. So this becomes our small signal circuit. We want to apply a voltage Vx and measure the current I sub x here. What we notice is that if we apply a voltage Vx, then this node is Vx here. These are both 1 ohms. So we know that this will be a voltage divider from here to here. So we'll just have that the voltage at this node will be Vx over 2. If this is Vx over 2, it gets multiplied by minus 10. We're assuming an ideal amplifier with a gain of minus 10. So this will be a voltage of minus 10 over 2 times Vx, which is minus 5 times Vx. So we now have the voltage here and the voltage at this node, which is at the gate of the transistor. We can now find the current I sub x. I sub x is going to be this current, which is Vx over 2, plus this current. And this current at the top here will be Vx minus negative 5 times Vx. So Vx minus negative 5 over Vx, which is Vx plus 5 Vx, and divide by 2 because Rs is equal to 2. So divide by 2. So this becomes our I sub x formula, and Vx, actually we don't need Vx anymore. This becomes our formula relating Ix and Vx. And we can then just find our out is Vx over Ix. Using that formula, we'll end up with this result here. Take it to the minus 1, and we'll end up with 2 over 7. So the impedance looking into this node here is 2 over 7 ohms. So that's doing full nodal analysis. But let's see if our loop gain analysis will give us the same result. So for loop gain analysis, we have the same circuit. We'll start off, let's just look at the loop gain when the port is open. So let's just look at L for a second, because hopefully that will come in as either the loop gain when the port is open, which we know will because that's what we're finding right here, and the loop gain when the port is shorted. So if we look for the loop gain here, let's say we break the loop at this location. We take whatever impedance was looking this direction and move it to the left. That will be 1 ohm in parallel with whatever we see looking up, and that will be 1 ohm in series with 2 ohms. This is opened to the right here, and this will look like a ground node since it's looking at the output of this amplifier, and will just be grounded because the left side has no current flowing through it. So if no current's flowing down through this will be at 0, and this will be at 0 as well. So we have the left side is 1 in parallel with 3 ohms. So when we break that, that's the impedance we'll put on the left side, and the right side will be the impedance looking into here, which is infinity. So we could put a resistor here of infinite value, but that's really just leaving it open anyway. So this becomes the breaking the loop properly. Now we want to find the gain around the loop. So if we imagine that we applied a voltage at this node here, V sub t, this to be multiplied by -10 to get to this point. And then the gain from this point to here is 1/2, since it's this impedance divided by this impedance plus 2. So it's just a resistor divider. So it'll be a gain of 1/2 going from here to here. Then another gain of 1/2 going from here to here. So if we looked at the loop gain then, what we'll see is the loop gain is just going to be 1/2 times 1/2 times 10. The negative 10 disappears because we have, remember, our loop gain is the negative of the gain, or the voltage around that loop. And that works out to be 5/2. So the loop gain for this circuit is 5/2. Next, we'd like to find the output impedance when we break the loop, which we've already done here. So the loop's already been broken here. So the output impedance that we're going to see will be the impedance looking down, which is 2 ohms, in parallel with the impedance looking up, which is also 2 ohms, because as I said, this will still look like a ground node. So that's just going to be 2 in parallel with 2, which is 1 ohm. Now we have that the loop gain when the port is shorted. So if all of a sudden I short this port here to ground, and I find the gain from here all the way around to here, well, because I'm going to be hitting the ground, this is always at ground, this is always going to be at 0 volts at this node. And if it's always 0 volts, the loop gain is always going to be 0. So we have that the loop gain when the port is shorted is 0. The loop gain when the port is open is L, which we found up here. So we just put these two together, and we saw that the output impedance is the output impedance when the loop gain was 0 times 1 plus L sub SH divided by 1 plus L sub OP. So it's 1 times 1 plus 0 divided by 1 plus 5/2. The 5/2 came from the loop gain up here. If you work that out, then you end up with exactly the same result when we did full analysis. So I went through this a bit slow. Typically you can go through it a little quicker, and you'll find very quickly that you can get this answer much quicker than you can do a full analysis, full nodal analysis on a circuit. So it was one example of a case where we had a shunt connection. Let's look at the case where we have a series connection. So in this case, we'd like to find the port impedance looking into this node, this node's here. So we can see we've taken our feedback loop and we've actually broken it and looking at the port impedance through that. So, and we're going to leave the same. RS is still equal to 2 and R naught is still infinity in this case. And A over here is still equal to 10. So it's a gain of -10 around the loop. Or the loop gain we'll be using a, not -10. It'll be a negative feedback around the entire loop. The negative feedback due to the negative gain from here to here, and this is still a positive gain. It's a non-inverting stage. It's just a source follower. Again, you can do full analysis, and I'm not going to go through it all here, but I've got some of the equations down. And if you do full analysis, you'll find that the output impedance is 14 ohms in this case. So it's quite a bit higher than what we saw in the previous case. Remember, the previous case was 2/7, so it's much less than 1 ohm, and now it's closer to 14 ohms. If we do loop gain analysis on this, we'll find that the loop gain, again, is 5/2. So if we short this here, so it's, in other words, we don't leave this broken, but we leave this connected here, then we know that the loop gain will be the same as the loop gain was in the previous case, because it's the same circuit. We've just looking at a series impedance rather than a shunt impedance. So the loop gain, we already know from the previous case, is equal to 5/2. We also have that the loop gain when it's shorted is the L, which is 5/2. The loop gain when it's open circuited, So if we leave this open at this point, because it's now open, you can see very quickly, let's look at this case here, that if I break the loop, apply the voltage here, V sub t, that this voltage here would just remain 0 volts because it's broken. There's no current flowing down through here. So if I leave this as an open circuit, which is LOP, then that's going to be equal to 0. If I leave that port open, we have a loop gain which will be 0. So that's this part right here. LOP is equal to 0. So the only thing we have to find here then is what is the impedance here when I leave the loop, when I break the loop but leave the impedance as correct. So in this case here, what we see is that the impedance we're going to see will be the impedance looking up in series with the impedance looking down, because this gets us to ground, and then whatever we have looking up goes to ground as well. The impedance looking up is 2 ohms, the impedance looking down is 2 ohms, so we see 2 in series with 2, which works out then to be 4 ohms. So the port impedance here when the loop is open circuited, or is broken, is equal to 4 ohms. And remember, because we're breaking the loop here, this is now just connected to ground. There's no connection between these two nodes here because we've set L equal to 0. And so if this is equal to just grounded here, there's no current flowing through it, so the voltage across this will be 0, and we have that that this will also then be 0 volts over here. So we have, this is 4, we can put it into our equation, that's 4. We have the loop gain shorted is 5/2, the loop gain open is 0. Put this all in and we get 14 ohms. And that's the same result if you did full nodal analysis on it. If you don't think this was quicker to do, I would encourage you to walk through and do this case here and see how long it takes you to do full analysis, especially if you do it without looking at the notes I have down here. It takes a fair bit of time to go through it. And in a more complicated circuit, it would take a lot more time to go through it. The other benefit is, even, remember, it's not all about just getting the answer. It's trying to get the answer with some insight. If you go through full nodal analysis, you'll get the correct answer here, but it doesn't tell you what happens as the loop gain changes. So as the loop gain increases, if I double L, you won't really see that in here. It's hard to see what's going on. Where this one's actually telling you that if all of a sudden I make L sub, this becomes 10 over 2 rather than 5 over 2, I'll approximately double my output impedance. So I'm seeing that directly the effect here of how my loop gain is affecting my port impedance. It's increasing it if the loop gain is non-zero when it's shorted and it's 0 when it's open, the port, then what I find is that my loop gain is increasing. Sorry, my port impedance is increasing. In the opposite case, if when LOP is non-zero and L sub S is 0, then my port impedance will decrease as my loop gain increases. So we see this decreasing and increasing case. Okay, so in this example, we want to look at a case where neither L sub S or L sub 0 is 0. So here's a case here where we want to find the port impedance now, looking across this resistor. And again, we'll let Rs equal 2 and R naught is equal to infinity for the transistor, same as before. But we're looking at a different node. Once again, you can go through full analysis. If you go through full analysis, you'll end up with the impedance actually is 13 over 14. So the impedance looking into this node here would be 13 over 14 ohms, a little bit less than 1 ohm. And again, you can walk through and go through all these equations here. We just want to see that we're going to get the exact same answer when we do loop gain analysis. So in this case here, this becomes our small signal model for this with the T model in for the transistor. We want to find the port impedance first when the loop is broken. So we want to find the impedance when we have this being broken. What we see as usual is that this node here is 0 volts. So the port impedance is going to be 1 ohm in parallel with the impedance looking up, in series with the impedance looking down. So this goes to ground, and then the ground comes back to over to the top of the 2 here. So it's 1 ohm in parallel with 3 ohms, which is 3/4 of an ohm. So you can see this pretty much by inspection. The loop gain, when this is opened, so if I do the case when I just leave this port opened, so I don't attach it at all, then we get exactly the same loop gain as we've always been getting, 5/2, because the circuit's exactly the same. But now we have the other case here when the port becomes shorted. So when I short this over here, if you go through the analysis here, what you'll find is that the gain from this node to this node is 10, as it was before, so that becomes the 10 factor. But now the gain from here to here is 1 divided by 1 plus 2, so it's 1/3. So this becomes 1/3. So now the loop gain when it's shorted is 10/3 rather than 5/2. So we have 2, in this case, we have LOP and L sub SH, and neither one has gone to 0. If we put this into the equation here, so we put in our normal R sub out is given by 3/4, which is this. We have L sub SH, which is 10/3, which is given by that. And L sub OP, which is 5/2, which will then be down here. Put that all together, work it out, and we get exactly 13/14 ohms, which is the same value we got when we did full analysis. So there's no approximations made here. You get exactly the same answer. Now, that said, what if our port impedance that we're trying to find has some extra resistance that's not in the feedback loop? So how should we deal with that? So let's say that we have this example here. So this looks very similar to what we had before, but we've added in this resistor, R3, equal to 1 ohm. We want to find the port impedance looking here. So we could use the loop gain method directly, and we could just say, look, we'll just either leave this open, and we'll find the loop gain when this is opened, or then we'll short it, and we'll find the loop gain when it's shorted. And so if we did that, we would do something like this. When it's opened, we would find that it is the original loop gain, and in this case it's 25 because we made A equal to 100. So we've changed A a little bit here. So A is 100 times the gain from here to here, which is 1/2, times the gain from here to here, which is another 1/2, so it's times 1/4. That equal to a gain of loop gain of 25. So the loop gain is the same as it was before, except multiplied by 4 because we've had this A is sorry, not multiplied by 4, it's multiplied. This A used to be 10, and which gave us 5/2 before, and now it's a gain of 100, which means that we have a gain of loop gain of 25 now. Now the port impedance looking in is just going to be R3 in series with the impedance looking down, which will be 1 and plus 1, in parallel with the impedance looking up. So we'll have R3 plus the impedance looking up, which is RS, in parallel with R1 plus R2. And that all works out to be 2 ohms. So that's still not too difficult to find. But the challenging part is now we still have to find, to do this correctly, we still have to find L sub SH. L sub SH is not 0. It's just now we ground this node here. And we haven't shorted the output. We haven't shorted this node right here. We've shorted it on the other side of R3. So there's still a loop gain in this circuit. We would have to go through the math and figure out what this new loop gain is. We go through all that, and you find the loop gain in the second case when it's shorted is actually equal to 12.5. So you find that then the output impedance is the impedance looking into it when L is equal to 0, or when we've broken the loop, times 1 plus L sub H, divided by 1 plus LOP. Work that out. Is 1 plus 12.5 and 1 divided by 1 plus 25. And we get exactly 1.0385 ohms. So we see it's slightly higher than our 1 ohm that we have here. And then we wonder, was there a better way to do this? Was there a better way to come about and find this impedance? So we did not have to do an extra calculation of L sub SH. And it turns out there is, because it would have been easier if we just find the impedance closer to the feedback loop and then include R3. So make sure that we only have to calculate 1 loop gain and not 2 loop gains. How do we do that? We just redefine a node, an impedance over here. This is the exact same circuit. We want to find R out, but to do that, we will find first this impedance, and then we just have to add 1 to it to get this impedance, because we have that R out is equal to R01 plus R3. So then what we expect is hopefully it's much easier to find this, because then either LOP or L sub SH is going to be 0. And if 1 is 0, then we only have to calculate 1. So for this, we have that R sub O1 comma 0 is the impedance looking down in parallel with the impedance looking up. That's going to be 2 ohms looking down in parallel with 2 ohms looking up, so it's 1 ohm. So we have that from before. We have that L sub SH, when I short this, that's going to make the loop gain go to 0. So this term here goes to 0. So we have 0 here. The loop gain, when it's open circuited, is the same one that we've seen before. In this case, that's equal to 25, because we're using a value of A equal to 100 here. So we have that's equal to 25. So we can quickly find that this R01, this impedance, is just 1 over 26, just using this equation here. And then we find that R out is equal to R3 plus R01, which becomes 1.0385, which is the same as we had before. And we only had to find 1 of the loop gains in this case. The other one was 0, so we only had to find LOP, and L sub SH was 0. So in general, we try to find port impedances that are close to the feedback loop, such that one of L sub SH, either the loop gain when it's shorted or the loop gain when it's open, goes to 0, and the other one is just a regular loop gain. So let's revisit example 3. We could say we took a little bit of time in this case over here. This example here, we found that we needed to find both LS and LOP. O. So L sub SH and L sub OP. So let's move our 1 ohm resistor to the right. And let's just redraw this schematic slightly. So revisit example 3 as this. So now we have R1 just moved to the right, and we'll find R out prime here, and then R out here will just be equal to R out prime in parallel with R1. So we try to find R out prime instead first. So for R out prime, to find that, we first look at the loop gain when the port is shorted, and that is going to be the gain from here to here. Remember, this is now shorted, and which is going to be this impedance divided by this impedance plus our 2 ohms. So 1/3, and times the gain A over here, which is 10. Actually, the gain A over here should be 100. Oh, sorry, it was example 3. I'll go back to that. Oh, in example 3, A was equal to 10. So yes. This is example 4 where A went to 100. So A is equal to 10. So we multiply that by 10. So the loop gain, when it's shorted, is equal to just 10 over 3. The loop gain when it's opened, so if we leave this as an open circuit from here to here, it's just broken, then the loop gain is going to be 0. The impedance, so R out comma 0 prime, will be the impedance 1 ohm in series with 2 ohms. So it'll just be 3 ohms. So finally we have that R out prime is this R out prime comma 0 times 1 plus LSH, and divided by 1 plus LOP, 3, 1 plus 10 over 3, 1 plus 0, it's 13 ohms. So the impedance looking into here is 13 ohms. That's in parallel with this 1 ohm resistor here. So we have that the actual output impedance is R out prime, which is 13, in parallel with R1, which is 1. And so we have that our final result is 13 over 14 ohms, which is the same as we found in the original example 3. So the moral is it's easier if you move closer to the feedback loop to find your port impedances, so that one of L's SH or L sub OP goes to 0. That's the end of these notes, and thanks for watching.